Hi, everyone. My name is Fedorishin, and I'm going to be presenting the 2021 DCASE workshop paper that was accepted called Waveforms and Spectrograms, Enhancing Acoustic Scene Classification Using Multimodal Feature Fusion. And so before I get into the actual paper, I want to frame the question it's based upon. And so what we really asked is waveforms or spectrograms. And what I mean by this is that there's two parallel paths in current literature for acoustical machine learning right now. And that's one path is using spectrograms and two-dimensional convolutional neural networks to perform acoustic processing. And the other path is using raw waveforms with one-dimensional convolutional neural networks. And so each of these audio representations, they have their advantages and disadvantages. So spectrograms are a lot more computationally efficient and they are more concise. However, waveforms are, they're very highly dimensional and extremely complex. But at the same time, spectrograms often discard phase information while waveforms inherently have that in the data still. And when you actually look at the first layer of a waveform-based model, what actually is happening is the kernels are being learned to be frequency selective filters. So it's really analogous to the FFT operation that happens, but instead of using kernels based off of the Fourier basis, we're actually using learned kernels within the network. And so really the question we're asking is which audio representation works better for classification? Or even further, can both of these representations be used to extract some complementary information? And the data set we perform our work on is the acoustic scene classification data set of the 2021 challenge, which is task 1B. And so we use the TAU audiovisual urban scenes data set. And this is the task of classifying environmental scenes from audio and video. And so in this data set, there's over 12,000 recorded audio and video samples spread across 10 classes or 10 scenes. And the authors provide a training validation split that we use. But a big note of this paper is that we only use the audio modality for performing acoustic scene classification, and we discard the video. So our proposed method really boils down to a model we created, which is an end-to-end fusion model that utilizes the raw waveform and MEL spectrogram representation of an audio sample. And so if we look at this figure to the right, we see essentially there's two different feature extractor branches, the waveform branch and the spectrogram branch. And each of these branches output their respective latent representations, LW and LS, standing for the waveform spectrogram branch. And what we do is we perform an element-wise summation of these vectors and then input that new vector into the classification layer for the final classification. And so if we look at this formula, essentially what we're saying is the classification of a waveform and a spectrogram is this, where we input the waveform into the feature extractor for the waveform, spectrogram into the spectrogram branch, and then perform the final classification. And in terms of this paper, we actually introduced two more networks to really understand the dynamics between using a waveform or a MEL spectrogram. And so we have the entire fusion model, but then we have what we call a spectrogram subnetwork, which is essentially the entire fusion model without the waveform branch. And then the opposite again for the waveform. And so what we're attesting is really to see how does the fusion model compare to a model trained only on MEL spectrograms and only on waveforms, and to really see the dynamics between them. And here's a little overview of our pre-processing and training pipeline, but I really want to point out the data augmentation that we use. So we use both time shifting and mix-up. And so for time shifting, what we do is we have a different time shift across each of the modalities. So for example, a waveform may be shifted 50% of its length, which is rolling the sample forward or backwards 50%. And then maybe the MEL spectrogram is shifted only 20% forward. And so these can be different for a single sample. However, for mix-up, what we do is we mix up two samples to the same degree. So we take one sample's waveform and spectrogram and another's waveform and spectrogram and mix them to the exact same degree. And so in our case, we have alpha set to 0.2. Looking at our results of our paper, we see that features are really being learned from each branch that are actually complementary to each other, and that fusing them together for classification improves performance beyond any of the single modalities, so beyond waveform only or spectrogram only. And If we look at this figure to the right, we see that both the waveform and spectrogram get around 64, 65, 66% accuracy, while our fusion model gets about 71% accuracy. So we see about a 4 to 5% jump in accuracy when we fuse these features together. And what we did is we also tested various other fusion methods. Instead of concatenating latent vectors, we could do score fusion, early map future fusion, and we saw that the proposed design that we have performs the best in terms of accuracy. And so another big part of this paper were the insights that we got from the ablation studies. So what we really learned is that when training this fusion model end to end, each of these waveform and spectrogram sub branches learn disparate features. And the way we noticed this is we saw a large performance drop when we removed one of the branches in the fusion network. So if you think back to that fusion network, there's a 2 branches and then the classification layer. So for this study, what we did is we cut away, for example, the waveform branch, and we see how the spectrogram branch performs when it was trained in the fusion setting. And so if we look at this table 6 on the right-hand side, we see that the spectrogram branch in the fusion setting actually performs much worse than when it was trained independently. And same thing happens with the waveform branch. And so what we infer from this is that there are really disparate features being learned when it's trained end to end. And when it is fused together, it improves performance. And another thing we notice is when we look at the actual class-wise losses in the model, we see that certain classes have a lower loss in a specific branch compared to the overall fusion model. And so what this is kind of telling us is that our current fusion method isn't optimal, but there's a few classes where the fusion method kind of averages out the better performing branch with the worst performing branch. And so what we really infer is that a better fusion method or a more discriminative fusion method can better exploit these features, and that can further improve acoustic scene classification performance. And overall, as a conclusion, we present a novel acoustic scene classification model that fuses complementary features of the raw waveform and MEL spectrogram. And so we validated that our fusion design outperforms other tested methods, and that each subnetwork does learn disparate but complementary features that improve performance. And we submitted this work to the 2021 Challenge Task 1B, and we got first place according to the validation accuracy metric, and then second place according to validation loss. And some future work we have is further investigating that notion of consistent data augmentations that I mentioned before, and then exploring other fusion methods as well, and even further really investigating the visualizations of kernels, filter kernels, and the embedding space to really see what's happening behind these fusion models. And that's really all we have. If you have any more questions, please read the paper and reach out. I'll be happy to answer any questions. Thank you. Bye-bye.